An aluminum company can develop their own alloys, but if they want to register it, they register it with the Aluminum Association, which is a trade organization based in Washington, D.C., and then it becomes sort of a national standard. And then eventually some of these become international standards. There's a whole hierarchy out there of buying and selling, yes.
What about proprietary alloys?
Proprietary alloys, for example, I'm involved right now in a problem between Alcoa and Boeing, not Alcoa and Boeing, but Alcoa and another company that stole 50% of Alcoa's business for aircraft wings, okay? And Alcoa's not happy. They laid off 600 people in January 1st because they lost 50% of their business. They make the wing spars for Boeing, for Airbus. Essentially, they had sort of a semi-monopoly, okay? And there are two primary alloys. One's the 2000 series, one's the 7000. It turns out the 7000 series, they actually they sell it as 7150. You can look on the web and find out the aircraft wings are 7150 alloy, which is an Aluminum Association designation, but Alcoa has a tighter spec that they actually make them to, okay? Internal spec. That's a trade secret, okay? So that's true in a lot of these cases. A lot of these specs in the ASTM standards came about 60, 70 years ago, and we've learned to improve our metallurgy in the plant, and we can make things to a tighter compositional control than we ever did before. And a lot of companies do that, and that gives them an edge in the marketplace, and they hold that generally as a trade secret. Okay, how to do that. But by the same token, if you want to order A516 steel for a pressure vessel, if you put on the purchase order A516 steel, I don't know how many pages long this thing is, but it's 3 or 4 pages long. You don't have to write all this stuff into your specification. You just reference this in one line, and you just increased your specification by 4 pages, right? This is incorporated in your purchase order. Yep.
So on the aluminum side of the house, would that just be Alcoa going to Boeing, whoever, saying, hey, we make 7100 series, but we make 7100 series, less turbo.
Yeah, I mean, to give you a little more detail, and this is not the proprietary part of this, Boeing and Alcoa have a contract, just like Airbus and Alcoa have a contract, and they have to keep that information confidential. Alcoa can't go tell Airbus what Boeing's telling them, okay, because that's Boeing's trade secret. And same thing, they can't tell Boeing what Airbus is saying. So they negotiate with each other. They have a contract. Boeing has to be able to audit. And you guys are soup ship. You're just auditors of the purchase that NAVC went out and purchased a ship, and you're there to do the quality assurance audit, right? If it's Bath Iron Works, they're doing the quality control, and as the fabricator, they're responsible for building the ship and making sure it's of the proper quality. But you got a whole building up there in Bath for the Navy, officers that are assigned there and the civilians working for the Navy who are going out and looking over the shoulders of the quality control inspectors at the ironworks. And they spend their life in meetings arguing with each other, right? Okay, trying to decide who's right and who's wrong. Ultimately, the Navy's got the checkbook and they're always right, but by the same token, they can burn you, okay? So you might as well try to cooperate. Okay, it's this interesting dynamic. I'm glad you guys get to spend your life in meetings like that rather than me. But in any case, you can specify these things. What was your question about the aluminum again? I'm sorry.
So it's kind of, does Alcoa submit like an additional spec sheet with theirs?
Oh, yeah. So what happens in this particular case, okay, Boeing is allowed to designate one person that gets to know everything about Alcoa's process. That person cannot even tell all the other Boeing people unless they're in a meeting with Alcoa and, Alcoa approves it. But that person is the auditor, because Boeing has to know what's going on. But in that case, only one person, in theory, knows everything from Boeing's side what Alcoa does.
So in terms of designing the airplane, do they use standard aluminum numbers, or do they use?
I don't know. I'm not sure I've gotten into that in that kind of detail. Okay.
With the 7100 series, because they'll do it, but if you shave a percent or two of weight in the 7100 turbo, it's probably worth it.
Well, it turns out there's other players. There's the Federal Aviation Administration. And the Federal Aviation Administration has a handbook, which used to be known as Mill Handbook 5. Okay? In the old days, Mill Handbook 5, and it's about 12 or 13 volumes and takes about 12 inches of shelf space. I have it. A few years ago, you could download the digital copy for free, and you could purchase the hard copy from the government printing office for $110, because that's what it costs to print it, even though it's 12 volumes. Some of them are thin, some are thick. But by law, if you're building a commercial aircraft, the FAA requires you to use the material properties as defined in that handbook. And it will have about 20 pages on the properties of 7150 alloy. Now, whatever Alcoa and Boeing choose to use, if they're going to tell the FAA that they're using 7150 alloy, it has to follow within that universe of properties defined by that specification, which is now metallic materials properties. Anyway, in the dual use stuff, they got rid of Mill Handbook 5, and now they've sort of turned it over. It originally had been developed by the Defense Department and the Federal Aviation Administration in cooperation, and now the Defense Department's sort of taken over the management of it to the FAA. And now you can buy it for $800. And I think it's $850 for hard copy, and it's $800 for the digital copy, which costs whoever's doing it nothing, right, to give you to produce, okay? Right. So, I mean, this is another problem with codes and standards. In the last 15 or 20 years, private organizations, the government is not allowed to make a profit on these things, but what they've done is they turned it over to a commercial outfit to manage the dissemination of this, and those people are making a fortune, okay? I mean, they're raping the rest of American industry, and it's written into law. Alcoa, if they tell the FAA they've certified this aircraft to the 7150 alloy, the Aluminum Association alloy, they can have a tighter spec between Alcoa and Boeing, but it has to fit within the 7150 umbrella. Does that all make sense?
So
Okay.
what advantage does Boeing have to use something that's better?
Because
take credit for it being better.
These are complex shapes, and they do it by stretch forming of the spars, okay? And Alcoa does that. Boeing owns the dies, okay? This is not proprietary. Boeing owns the dies. Alcoa stretches the aluminum extrusion over the dies to a particular shape, and when it gets to Boeing, it fits right into their jigs and fixtures for machining. And if it didn't, they would be, in a shipyard, how you got all these jacks and come-alongs to get the thing to fit. Well, this is fairly precise machining on an aircraft wing. More precise, actually not more precise than a ship. Did you know that building a ship is the most precise manufacturing operation we have in terms of parts per thousand? Okay? If you tried to machine a 1-inch diameter shaft, anyone should, in a regular machine shop like we have across, down the hall here, be able to machine to half a thousandths, 1 part in 2,000. What's the tolerance in building a ship that's 100 yards long, 300 feet? It's 1 part in 20,000. It's about 10 times more precise. The only thing that rivals it is building a semiconductor chip where we have nanometer technology, right? And that gets down nowadays to about 1 part in 20,000. So really small or really big.
So you spread out those tiny little problems over 700-800 feet.
Yeah, I mean, You calculate what happens when the sun comes out from behind the cloud down at Ingalls, okay, and the ship, in changing its dimension as the sun heats one side of the ship as the other, and all of a sudden those things you just aligned within a quarter of an inch are now off by half an inch, okay? And it's just the sun coming out. And when it goes back behind the cloud, it shrinks back the other way, okay?
We had some support columns get blown out at Newport News because of that, actually. The sun came out in the winter and heated up the flight deck, and it caused the ship to hog.
Yeah.
And it blew out the columns at the stern of the carrier.
Yeah, see? Isn't it great about some things you have to worry about? And most people don't realize that shipbuilding is one of the most precise industries. If you go through it, you don't really think it's so precise, okay? But you start calculating what you have to have for tolerances. And what I was looking for, I thought I transferred it over to my Dropbox, but obviously I didn't. I had Spac Van Lamming, he was the William Taft of last year or 2 years ago, whatever. He's one of the 2N students that was the leader of, the oldest guy in the class, as we say, who was coordinating things. And Spac did one on modular submarine construction. Okay, it was just a bunch of pictures, but it showed the modular construction. It showed a module, a cylinder of a sub that had been built up at Quonset Point, being taken down to Newport News on a barge, and then how they put it together and stuff. So anyway, submarine construction is not submarine, but ship construction is more precise than most people think. So, have I answered your question about where the numbers come from? Okay, it's a very complex process, and that's what my codes and standards module is about. Is how some things have force of law, some are consensus standards, others like Pirates of the Caribbean, it's just guidelines, really. You don't have to follow it. They have recommended practices. American Petroleum Institute's very big on recommended practices. So Brian, you want to tell your story about under deposit corrosion and Hurricane Sandy?
As a follow-up to the corrosion talk yesterday, so I was doing a consulting job at a World Trade Center, and it was their sewage ejector pumps and sump pumps down in the basement level. So they're cast iron, which is iron with 2 to 4% carbon added. So we take out the cast iron component and we cut a cross section, look at it, under the metallographic microscope, and all you see is it's a spongy material. So what you're getting there was graphitic corrosion, very similar to selective leaching, dealloying that you see with brass's dezincification. But this is for cast iron. So what happened was you had Hurricane Sandy, you had seawater, and they never flushed out those lines. So you had millions and thousands of ppm chlorides in the pumps. So it was eating away at all the iron and cast iron.
What kind of timeline was that?
A couple of years.
Ordinarily, the cast iron will last for 100 years or more if you maintain it. Cast iron forms essentially a silicon dioxide, a glass surface. The passive film, cast iron's iron, 4% carbon, 3% silicon, and all that silicon forms a glassy layer on the surface. And so cast iron in water service, aqueous service, has better corrosion resistance than steel, which rusts. Steel doesn't have this thick, glassy layer. Cast iron does, but chlorides will eat through that, okay, when you start getting, under deposit attack. So one rule, which I didn't put in my list of rules on corrosion, is cleanliness is next to godliness, okay? It helps to keep things clean, okay? So let's see, what else do I want to do? So I covered that, I covered the schedule. Okay, I can just move things over here, okay. And I showed you some typical student presentations. Don't worry a whole lot about the specific student presentation. Okay, we had talked before about fracture toughness, and I had neglected to bring my the rubber pieces. Remember I talked about you put a little notch in something and it reduces strength by 80%. Well, if it's a ductile material like rubber and you pull on it, it doesn't just propagate that crack, it blunts the crack. You don't get a sharp notch for a stress concentration, it just sort of deforms. And that's what steel does, ductile steel. There's also brittle steel. And I got to analyze this someday. A dozen years ago, I asked someone, go in the lab, get me a sheet of metal, or a sheet of rubber, and I want to test something. This stuff is the toughest rubber I've ever found, okay? I pulled on this as hard as I can't get this thing to propagate. It's all stretched and everything, but I've spent several $100s buying all kinds of rubber to get something that's as good as that. This one, this red one, I could actually, if I pulled on it hard enough, I could get it to break. But this other one, boy, it's tough, and I haven't figured out what it is. I got to do an analysis on it sometime. But rubber analysis is not easy to do. Let's see what else we got. Okay. So, what I did want to do, and this is more like a recitation day in some ways because I wanted to pick up on a few things. There are 2 books, and you guys have a better allowance than people did 5 or 10 years ago in your class?
We don't have any.
You don't have, oh.
They took the book allowance away a couple years ago.
But you did have a little library over there at one time, right?
We've
Yeah.
got some books there. I don't know if I can call it a library.
Okay, well, I did buy I bought some books for you guys once, but for over there. But in any case, let's see if I can do this quickly. Switch over. So these are the Nalco Guide to Cooling Water Failure Analysis and the Nalco Guide to Boiler System Failure Analysis. Nalco is the world's largest water treatment company. They're like $4 billion a year, and they go around. If you've got a boiler, they'll take the contract and they'll take care of maintaining your water chemistry, okay? Navy does that themselves. They don't contract out to Nalco. You got enough water systems that you can do it yourself. So, and these books, they're published, they're now in the 2nd edition, and they're published by McGraw-Hill. This one, I had the 1st edition before. This one, I just ordered, and it came in yesterday. I saw it at my secretary's desk after class. But in fact, there were enough things in here that had to do with yesterday's lecture that I thought maybe I would bring it in and we could talk about some of them as sort of a recitation of what we were talking about in corrosion yesterday. We talked about condenser tubes, or I mentioned some things about condenser tubes. And these are some of the materials from the very beginning of the book, some alloys for heat exchanger tubing. Okay, condenser tubes. And so copper's got the best thermal conductivity. You're trying to transfer heat, so you'd love to use copper. And if you got good, really clean water with no solid particles in it, they're going to cause erosion. Copper would be great. Aluminum is good, but it's pretty soft and would erode away. Although aluminum is very good, has very good corrosion resistance in sewage. You go down here to the sewage treatment plants here in Boston, all made out of aluminum, okay? Because the pH is not, it's somewhere near 7, okay? And aluminum is very good. We'll see why a little bit later. Yellow brass, that's what people used to use, okay? That's number 3 in thermal conductivity. Admiralty brass and aluminum brass are alloyed a little bit. We lose a little bit, but the aluminum brass has this good aluminum oxide skin. And so it has good erosion resistance. I passed around that kind of prototype propeller. So manganese aluminum bronze is what the Navy uses for ship propellers because of the, not thermal conductivity, but So that's basically what people, who was Admiralty brass, they were using 30 or 40 years ago at Baltimore Gas and Electric, where they had this under deposit attack I was talking about. And you can use nickel, kind of pricey, but it's still got pretty good corrosion resistance. Of course, carbon steel, we all know it rusts. And then the Navy likes to use cupro nickel, okay? Cupro nickels, although they tend to like to use the 7030s or the Monels, which are 3070 cupro nickel, if you will. And now you're really biting the dust. You can use stainless steel, it tends to pit. Titanium is better than stainless, and it's got fantastic corrosion resistance, we'll see. And if you have to go to really high temperatures, not well beyond water, you can use some of the nickel-based alloys. But I mean, there's a whole host of materials. And if you're talking about condenser tubes or boiler tubes, these are the types of materials you use. And of course, if you're talking nuclear reactors, if you're talking boiling water reactors, typically used in stainless steels, you're talking pressurized water reactors, we're getting into the Inconels, okay? Just has to do with the operating temperatures and conditions.
For layman's terms, what is cupro nickel?
Cupro nickel is just copper nickel alloy. Okay, sorry, it's 90% copper, 10% nickel. Okay, and the Monel 400 is a 30% copper, 70% nickel. So if you go across the copper nickel phase diagram, you got 90-10, 70-30, 30-70. The Navy uses lots of Monel in their seawater piping. Good corrosion resistance. Not fantastic. I told you the story about the aquarium. Stainless steel wasn't good enough. Monel was somewhat intermediate in maintenance and everything else. And titanium would have been the best, but it's pricey. So it's a complete trade-off there between price and performance and maintenance and things like that. So, and more, the Navy is starting to go towards titanium for piping, because now you have 50-year ships. Not when you had 30-year ships, then you would use carbon steel for your seawater piping. But now they started going to some of these higher alloys, copper nickel alloys. They never would have gone stainless steel because it'll pit like mad if you get any dirt in there very quickly. That's the problem at the New England Aquarium in a sense. But now they're even going titanium because we're looking for 50-year lives. Yes?
So do you get better thermal conductivity in titanium since the walls, I assume, would be thinner than
Yes.
the other ones? So
Yes.
The coefficient, the conductivity coefficient's lower, it's still better.
You can use, because it doesn't corrode and you don't have to have extra corrosion allowance on your thickness, you can use half the thickness, okay? It's also stronger, you can use less thickness. Maybe you even use a third of the thickness in some cases, but you're talking about material that's going to cost you $70 a pound as opposed to $7 a pound as opposed to carbon steel at 70 cents a pound, okay? So the price is, yep.
We said at the previous lecture that we are replacing the yellow brass tubes and heat exchangers with titanium ones, right?
Right. Well, more and more industry is.
Will that increase the size of heat exchangers since the thermal conductivity is almost the 1/6?
No, there's lots of things you can do in design to compensate for the lower thermal conductivity. Well, yeah, you can have plates, turbulators, because it's not all the material conductivity, it's the boundary layer inside the tubes, okay? You gotta worry about, this is where your fluid flow comes in, guys. You gotta worry about the boundary layer, so you start turbulating the inside of the tubes, putting little ribs in there so that you get heat turbulence. Pardon me? Oh, yeah. I mean, yes, they basically, if you go, well, if you look it up on Google, you'll find.
Does it add stress points in the tubes or the exchangers where corrosion might occur?
It could if you got deposits in there, but titanium doesn't care about the deposits. Those tubes in cross-section would look, and they have little fingers on them, like this. Okay, I'm not going to draw the whole thing, but I've got one, and this one happens to be copper in an air conditioning system at a hospital down south of here, and this might be 0.5 millimeter. And these little ribs might be 1/3 of a millimeter, and they might be 1/2 millimeter high, okay? And they're just fins for better heat transfer. So we can do a lot geometrically. This is just material property. There's a lot you can change the diameter of the tubes, you can change the water flow rate through the tubes. Although, if you change the water flow rate, I had a heat exchanger up here at the Mormon Temple in Belmont, and they originally had put in copper as the heat exchanger material, okay? And after 1 year, they knew they had a little leak in there somewhere, and so they took the top off, and up at the tube sheet, the plate that holds all the tubes, where everything had turned because of the higher speed, they had corrosion on the copper because of the solids in the water and stuff. It caused erosion. And I wanted to go to 7030 Cupro nickel, but they couldn't get that. They had a 2-week shutdown. You guys know the shutdown procedure. They had a 2-week shutdown. They discovered it on the 3rd day of the 2-week shutdown. They had to get a new heat exchanger in so they could be up and running in another 10 days. Turns out the people who sold it to them originally charged them $16,000 for this tube sheet, set of tubes. It was a small heat exchanger. It's about the size of one of these desks. And they found, the manufacturer was down here in Rhode Island, and the manufacturer would sell them one for $6,000, even though the original people charged them $16,000, a little bit of a markup there. Anyway, but they had in stock, and down here in Rhode Island, 9010. And I said, well, you got to get up and running. Let's put in the 9010. And it turns out the 9010 has worked just fine, okay, for the last 15 years. Now, I haven't looked at it since then, and I didn't know. I was being a little conservative when they said, okay, we want to, how do we solve this problem? I said, you need to go to 7030 because I knew from the velocity data that 7030 would have had enough safety factor. Couldn't get it, used 9010, and it's worked. So, okay. But the real thing is it only cost them $6,000 for the replacement, which I thought, I don't know if you want to use that contractor next time. Marked it up $10,000 on a $6,000 part. Other questions? Okay, here's another thing on which we will go over when I get back to the corrosion lecture. In fact, this is a nice slide out to incorporate into my thing. This is water chemistry versus steel corrosion rate in thousandths of an inch per year, mils per year. And I always say, in fact, you'll see my presentation later, we haven't gotten to it yet. I say typical corrosion rate of steel in water is 0.004 of an inch per year. Okay, I got lots of stories. About once a year, someone comes to me and says, our steel rusted. Oh yeah, really? And we need you to tell us, did this occur in 2 weeks, 6 months, 3 years, 20 years? And all I do is I divide the thickness by 4, okay, 4 thousandths, and I say, well, this took about, if they lost 100 thousandths, I say, this took about 25 years. And they say, oh, how'd you get that? Well, you divide 100 thousandths by 4 and you get 25. I learned this in elementary school, folks. I mean, this is not that difficult. But this is actually a more detailed plot. ISO corrosion curves for steel as a function of alkalinity and calcium concentration. Well, what's all that mean? This is the hardness of your water, and this is the amount of sodium and CO2 basically in your water chemistry. And you can see there's kind of your average. And I always say it's 4 thousandths, but if you look in the literature for corrosion in some place like Arizona, it may only be 2, and in a really bad industrial atmosphere, the water, it might be 10. And one time in Arizona, I saw it was 20, but that was up in the roof of a building. And it was a big warehouse, about 1 million square foot warehouse, and they had had a big rainstorm in Phoenix while they were building this. And all the insulation got wet before they put the decking on. So what did they do? They put the decking on, and they already had a bottom seal. So they had about an 8-inch height in that ceiling of a little greenhouse, okay? And the sun would come out. Did you know the sun comes out in Arizona, in Phoenix? And it gets hot. And they had a little, every day and every night, they basically would just bathe this in wet, water, hot water. And so they actually had 20 thousandths of an inch a year. And when you got, galvanized, the galvanizing went away in months, a few months. And then the sheet metal in the steel, which was only 60,000, 16th of an inch thick, 20 thousandths of an inch a year within 3 years, they had holes in their sheet metal. Leaky roof. It's only 1 million square feet of roof. What's that among friends, right? And it's because it rained, terrible downpour. Anybody ever seen Phoenix a week after the rain? Beautiful. Desert blooms. Yeah. Is it called Green Desert?
Yeah.
Yeah. I mean, I was in Phoenix once about a week after it rained, and it's beautiful, okay? All it needs is a little water, okay? And that's what they have there, a little water. So anyway, that's just corrosion rates. What's this? Okay. Oh, this was kind of, you asked me about stainless steels, and this is actually, this is a list of commonly used grades of stainless steel. You don't have to worry about this. But these S numbers are the International UNS, Unified Numbering System for Alloy Numbers. So yes, originally you had 304, which 100 years ago the American Iron Steel Institute said 18.8 stainless steel is 304, and 18.8 with 2% molybdenum is 316, and they give these numbers. Well, then about 25 years ago, they came up with a UNS alloy number. And in Europe, they have an International Standards Organization number. There's big competition between North America and Europe for who's going to control the standards, because it makes a big difference economically. If people in India are ordering a boiler and pressure vessel to the American Society of Mechanical Engineer standards, they're going to end up using the American standards for the steel specifications, and that gives the American steel companies an advantage. Actually, it gives them no advantage because it's going to be coming from Japan anyway. But that's another story. Okay. Pardon me? What were you saying? Okay. But, in any case, here are a lot of the grades of stainless steel, and they will give you the compositions and the ranges. And if you look in here, 304 is 18 or 19, 8 or 9. Okay. These are the ranges in silicon. It gives you the compositional limits. And there are dozens and dozens. And if you look in the Metals Handbook, it will give you the non-standard grades, which are the proprietary grades, okay? Sandvik, a Scandinavian company, makes a lot of stainless steel, especially stainless steels, and they haven't submitted to the American Iron Steel Institute for a designation. They'll have a UNS designation, but they may not have the old American Iron Steel Institute. And this is another page. There's different types of stainless steels. Martensitic, like this is a Martensitic stainless steel. This is 30 years ago. This is $300 pair of scissors made by Johnson & Johnson for surgeons. So it's a $50 pair of scissors with cobalt inserts brazed in for wear resistance, so it keeps a nice sharp edge. Gold-plated handles, because you're going to charge $300 to the surgeon, and $270 worth of life insurance or product liability insurance in case you get sued. Okay, about 90% of the cost of a lot of your medical products is insurance. Okay, for the lawsuits that are going to come about. Duplex stainless steels, for example. Anybody know where the Navy uses duplex stainless steels? Catapults on aircraft carriers. Need really high strength. I mean, the duplex stainless steels, they're basically a mixture of ferrite and austenite, but need really high strength. You can get very high strength, very good saltwater corrosion resistance, and that's what you need for the catapults, okay? Because I don't know, what's the PSI on catapults? 3,000 or 4,000 PSI or something, right?
Yeah. It's in the 400 to 500 range.
Well, maybe.
For the steam or for the hydraulics?
Yeah, I guess that's maybe what I'm getting confused
The
with.
steam is in the 400 to 500 range.
Yeah, okay. The steam may be 400 to 500, but some of the hydraulics are pretty high.
5,000.
Yeah, okay, fine. Anyway, whatever it is, I mean, there's different pressures and different things. I guess I had a problem once. Ferralium 255 is actually, or 2205. That maybe it's 2205. Actually, if we want to talk about stainless steels and corrosion resistance, we can talk about the Miami Art Museum, which is sort of a fun story. So Miami's building an art museum. It's about 100 yards from Biscayne Bay. And it's a hanging garden. Some guy in Switzerland's designing this. And up 6 stories in the air, they have these big concrete beams. And they're going to have, you know, since mold and green things grow all over in Miami, they decided to make it part of the architecture, right? So this is sort of supposed to be like the Babylonian hanging gardens, and people could sit out there on the veranda and sip their mint juleps or whatever it was, and have these concrete beams shielding them from the sun. The only problem was, as they were building this, they used a martensitic stainless steel. Someone specified I think it was a 410 stainless steel, because you could get very high strength, but without getting into all the metallurgy. Yes, they could get very high strength, but they actually were in a range that gave it low fracture toughness. And then they had to tack weld these things, and they did a tension connection. Why some idiot created a tension connection where you could have had something in a compression connection just laying on top, right? No, they put the beam that could fall underneath and then a stainless steel bolt holding it on. And so if the bolt failed, boom, okay, you got 20 tons of concrete landing on either mint julep and maybe you, okay? This was during construction. And so during construction, they erect these things, and they had some tack welds on there during the erection. And about a week later, a couple of them come crashing down. Now, this is during construction, nobody got hurt. And the architect says, well, why'd you weld them? And the guy says, well, you looked at your drawing? It had a weld on there, okay? This martensitic stainless steel is not very good for welding, okay? So they started looking around, and they decided, oh, we'll use 316 stainless steel, okay? And so this was in the fall. They had the failure. They had to have everything completed in this building by the next December for their grand opening and stuff. I got a phone call one Wednesday in March of whatever the year was, a few years ago. And I was working, the general contractor wanted to hire me to kind of look over the shoulder of the people doing the precast concrete and the erection, you know, with the stainless steel. And so he sent me some documents. I looked at them on Thursday. He was in my office at 7 a.m. Friday morning, which is the first day I could meet with him. And he says, I said, well, 410 was a terrible choice, just absolutely terrible choice for a saltwater environment and welding and everything else. And he says, well, they're going to 316. And I said, and the contract had a 1 year, the construction contract had a 1 year warranty. I said, well, 316 should last one year. May not. He says, well, will it last 10? I said, well, what's 10 years? He says, that's the statute of repose. The statute of repose is when you can no longer sue. Okay. But I said, well, I don't know if you're going to make 10 years on 316. Just shooting from the hip. And so he asked me why, and I explained there's something called stress corrosion cracking. We're supposed to be talking about corrosion, so there is some corrosion in this story. Well, so he goes back and he tells them, and they tell the engineer of record. The engineer says, well, this is not a saltwater environment. It's 100 yards from Biscayne Bay, which is saltwater, right? And they said, oh, it's not a saltwater environment. It says, excuse me? And they said, oh, no, it's 100 yards from the bay. Well, you don't have to be immersed in saltwater. And did you know they had hurricanes in Florida? And every now and then the ocean's coming horizontal at you? Okay, it's called rain. You know. Okay, so we had this big meeting, and the owners, the architects, the engineers were all shooting at me because I was telling them they had a problem, and they didn't want to hear they had a problem. But I sort of stood my ground. Now, the one good thing about it was the the architect's expert was a guy that I'd worked with for years here in Boston, with a firm here in Boston. And he's a concrete expert. He knows a lot more than me about concrete. But he accepts that I know more metallurgy than he does. And so he was sort of kind of telling him, listen to this guy. Anyway, I originally said, well, I didn't know how many bolts they had. I said, hey, if you just replace them with one of the nickel-based superalloys, cost you a lot of money. Well, it turns out they had $3 million worth of stainless steel, and this would have been $30 million, adding about $27 million to a $60 million building, which was not a good idea. So they started doing things. They went back to Sandvik in Sweden, and Sandvik said use the Duplex stainless steels. And they said, well, can we use the Duplex stainless steel? I said, sure, as long as you don't have any weld details. Can't weld this without real problems, okay? It's good for pipe and oil wells and gas, sour oil wells where you have hydrogen sulfide and stuff. So we went through several things. And again, everybody's asking me, even though I was the idiot who didn't know what I was talking about when we had the first meeting, everybody's now asking me to approve the design. I said, nope. I'm not being paid to take the liability for this building, particularly if it comes crashing down like the Hyatt Regency collapse, okay? That killed a couple hundred people. But I forced them to, I would give advice, but I was not going to sign off on it. There's an engineer of record who has to sign off legally on this design, and I was not going to assume that responsibility for the pittance they were paying me for consulting, right? I mean, if someone was going to allow me to make a couple $1 million profit, well, I could afford to buy some insurance, liability insurance. But anyway, those are other stories. So 2205 is what they have, and it's actually working, and they made their deadlines, and it only cost them about $7 or $8 million increase on the $60 million building. Okay, this is pitting of stainless steel. Let's see if we can't brighten that up. I don't know if I can brighten that up. Well, maybe I can just blow it up. Yeah, you can sort of see. This is, and this was in the first edition, but they didn't tell me much about it. There's a quarter. This is just a stainless steel beaker, which perforated in 64 hours. It's 304 stainless steel. That's 104 millimeters per year, okay? That's 1/10 of a meter. Okay? That's 3 inches a year pitting resistance. Due to exposure to water, it contained a chloride tablet, okay? That's thousands of parts per million, but it's not a huge amount. Here is chloride pitting resistance versus chlorine. This is 304, 316, 2205, okay, and pitting. And so this is what we ended up using at the Miami Art Museum, significantly better than 316 or 304, okay? This is, well, AISI 304 is down here, 316 is in here, and this is a 2304, which I don't even know what it is, and a 2205, okay. This is under deposit attack. Let me zoom down a little bit. So here we've got some crevice. You got a rivet here. You've got some crevice. You have different ions in one area than another. And this is what the localized wastage on a 316 stainless steel heat exchanger tube, okay, due to pitting corrosion. And there's the pitting corrosion that goes on and the chemistry, localized chemistry. Oh, I told you that you need oxygen to have corrosion. Well, here's a little thing out of Herb Uhlig's handbook. Herb Uhlig was the guy who started corrosion research here at MIT. You go up the second floor, it's the H.H. Uhlig Corrosion Lab, which doesn't exist anymore, but they have a plaque on the wall. Concentration of dissolved oxygen versus corrosion rate in milligrams per square decimeter per day. There are corrosion rates. Don't ask me why these people use these things, but that's what they used back in the 1930s, okay? Effective oxygen concentration on corrosion of mild steel in slowly moving water containing 165 parts per million chloride, okay? And pretty good correlation, okay? You need oxygen to corrode. This is some dealloying on a condenser tube or whatever. Remember, this is a book on cooling water systems. And this is the dealloying. I mean, this is a pitting dealloying, the dezinkified in this area. And then all the way through here, okay? And it gets spongy, porous. This is some pictures of exfoliation corrosion we talked about in aluminum, 7075 aluminum, okay? And it's just flaking off in layers. This is a vertical view of a exfoliation corrosion, and you can see it. It really is like a Greek pastry, okay? This is a wedge-shaped fissure due to corrosion fatigue. Basically, the crack opens up on the first stress cycle. It starts to oxidize on the next stress cycle, but as the crack grows, you get a wedge shape. So whether it's thermal fatigue or corrosion fatigue, you see these little wedge-shaped cracks full of oxide, and that tells you the mechanism, okay? Here's another thing that talks about effective chloride concentration on susceptibility of type 304. Test time in hours versus the cracked specimen cumulative. So I got a bunch of specimens, and you can see as you march up from 10 part PM chlorine, that's basically, if you condense the air in Cambridge, Massachusetts, because I've done it, and measure the chloride, it's 5 ppm chloride here. The drinking water, which is pretty good in this area, except in the winter when they're putting salt on the roads, is around 10 or 20 parts per million chloride. 100 parts per million chloride, you're getting to the EPA drinking water level. 1,500 parts per million chloride, we're getting into the brackish water area, okay? And obviously seawater is like 30,000, but you can see, test time, this is a log scale. So your stainless steel, this actually is our hot dog cooker, okay, in a sense, okay? Lots of chlorides in those dogs, and 304 just couldn't cut it at the high chlorides and failed within days. Okay, so anyway, I got back to my office, had this new book, and flipped through it and put all these post-it notes on and said, oh, this is all kinds of things that kind of reinforce the types of things we were talking about yesterday, okay? Chlorides are bad for lots of materials, not just stainless steels. Any questions? I need to ask more questions so I could digress more. But anyway, okay, so tomorrow we will go back to the CAN slides. This is the type of lecture I used to give, okay, using my little thing and throwing books up here and wandering around on things. And I will appreciate your feedback on which ones you prefer, or does it not make a difference? You know, he was incoherent anyway, so I mean, what do we care? We're not being graded, so what do we care? Okay, thanks.
I have a question.